Assalamu alaikum. There are various ways of calculating the required sample size for a certain study depending on the study design and various other factors. Therefore, there may be about more than a dozen different equations or formulas to calculate the sample size. This presentation is the first of 4 presentations on how to calculate the required sample size for the commonest 4 scenarios in which you would need to calculate the sample size before starting your study. The sample size would influence 2 important statistical properties. If we are doing measurements, the precision of our estimation would increase with the sample size increase. But obviously, we want to find which point the sample size would be enough to give us appropriate precision so that the outcome would be expressed on the average of our measurement, a margin of an error, and a confidence level. We will see examples for this. In this presentation, we are dealing with continuous data from a single group. We'll see examples about measurements of things like lengths, or weights, or age, or time, or enzyme levels, hormone levels, and such like. The other important statistical property is when we are comparing results from a certain group to a known standard or to another group to draw conclusions to say it's more or less or equal or related. This is hypothesis testing, and we'll see an example about finding out if the systolic blood pressure of adult epistaxis patient is more or less than the normal systolic blood pressure. Before starting a study on a single group measurement, we want to know the number required, and 3 factors would influence this. The number required N is related to the level of confidence that we want in our results, the variability of the measures within the group that we know from previous studies, from the literature, or from pilot studies, because we have not yet started our own study, and the margin of error that would allow for our measurements. The margin of error is set by the investigator. The level of confidence is also set by the investigator, and the variability, the standard deviation, is taken from pilot studies or previous studies. And the 3 factors would give us the required sample size so that at the end of the study we would have enough precision in your measurements to give the average, say for example 12 millimeters of a certain distance, and a margin of error, say about 1 millimeter plus or minus that average, with a level of confidence of 95%, for example, or 97 point something, or whatever. You set out the confidence level and the margin of error. And that applies to all measurements for continuous data, lengths, weights, and time and things. The confidence level would tell you if it is 95%, for example, that if the study is repeated 20 times, 1 in 19 times of the 20, your estimation of the margin of error and the average would fall within this line, which resembles the actual population mean. So you know that you have a high level of precision in your estimations. To take an example, say we are setting up a study to measure the distance between the posterior ethmoidal artery and the optic nerve in adults. We want to know exactly what is the distance, the average distance, and we will set the margin of error that would allow for, and that should be as narrow as possible. Say we choose to 1 millimeter because it is surgically important to have a very precise estimation about the distance between these 2 structures. So you would allow only for a very narrow margin of error, and you want to be very confident about the results, so you choose a 95% confidence, so that if this study is repeated 19 out of 20 times you would have within your margin of error, you would have the correct estimation here. All of these 19 different studies, only one study would have the margin of errors around the average outside the correct answer. So we start with the equation, and there are three variables here that would need to be identified. The first is the level of confidence, and we have chosen 95% level of confidence. The z-score for this is 1.96, so we'll put here 1.96. The standard deviation of the measurement between the posterior ethmoidal artery and the optic nerve from previous studies or from pilot study should be about 3 millimeters, so that would be plugged into here. And the margin of error that we have chosen, because we want to be very precise, would be 1 millimeter, and that would fall into here. And the equation would then this amount would be squared, and the required sample size would be this 34.57. This is the minimum. So the actual number of cases, either patients or surgical skulls or surgical specimens required would be 35 cases. Now, the second equation to estimate a sample size for a different scenario is this. It's the equation needed if you want to compare measurements in one single group with a standard, a known standard. Say if you want to measure a blood pressure, systolic blood pressure of a certain group, you can do this with only a single group. You don't need to get a control to compare it with, because it's already known. The systolic blood pressure in adults is already known. It's a known standard. So you can afford to have only one group and compare it with the known standard. The equation, again, depends on three factors. How much you would allow for type 1 error. This is the level of confidence you would choose. How much you would allow for type 2 error. This is how much power you need for this study. And the effect size, which is the difference between your group and the standard measurements divided by their standard deviation. So if you have a group which is quite different from the known standard, then you would have a higher effect size. If it is very close to the known standard, then you would know that it has a smaller effect size. The distance between the average of these two groups divided by their combined standard deviation would give you the effect size. So this is the second equation to measure sample sizes. So for example, if we are investigating the systolic blood pressure of adult epistaxis patient, this is an example of analyzing continuous data from a single group. You can do one of the two types, use one of the two equations. If you just want to get measurements, precise measurements of the systolic blood pressure in this group, then you use the first equation, and then you will be able to tell that the systolic blood pressure, for example, is 140 millimeters of mercury with a 5 millimeters mercury margin of error with a 95% confidence level. You get this out of this equation. This equation, which depends on the margin of error, the level of confidence, and the known variability and the blood pressure of this group. Here we set the z-score, the level of confidence, again at 95%. So z-score of 95% confidence interval would be 1.96. We'll plug this here. The variability and the systolic blood pressure in epistaxis patient or in patients in general, known from the literature or from pilot studies, would be somewhere around 20 millimeters mercury. So we'll plug this into here. And the margin of error that we want to allow or can allow would be, say, 5 millimeters mercury. We set up this level as much as we set up this level as well. So we'll plug in here 5 millimeters. So the equation will be 1.96. This is here multiplied by 20, the standard deviation that we have found in the literature or from pilot studies, divided by 5, which is the margin of error, all squared. This will give us 61.546, i.e. the required sample size would be 62, at least 62, because we have to consider patients who may be lost to follow up. So that's the first equation for the continuous data from single specimen. The other equation is this. Say now we have found out the blood pressure of the adult epistaxis patient with good precision in the measurement, but we're now interested to see if this systolic blood pressure is higher or lower than normal. Then we compare it to a known standard, and that known standard is fixed through the literature, the systolic blood pressure of adult patients. So we here compare our measurement with the known standard and find out if there is a significant difference or not. And for this, we need the required sample size, which depend on the 3 factors: the level of confidence here, 95% again, and the power of the study. Here we have chosen 90% power of the study, which translates to z-score of 1.28. So we plug this here as well, divided by the effect size. Now, how can we measure the effect size? And with a single group, we subtract the average of our group from the known standard. Say if we have measured the systolic blood pressure and the epistaxis is 130, the normal systolic blood pressure in adults is 120, so that amount would be 10 millimeters divided by the known standard deviation, again from the literature or from the standard, and that's 20 millimeters mercury. So if you divide 10 by 20, this is half. Effect size here is half. So plug in 1.96 here, which corresponds to the z-score of 95% confidence, and the power 90% is 1.282 divided by half here, and this would give you the result. Required sample size is 42.04, which is 43 patients. We've been through 2 equations to estimate the required sample size for a single group study. The first equation was for precise measurement of continuous data with a certain degree of confidence and a narrow margin of error. And the second equation was to compare a single group with a known standard, again with a known level of confidence and a certain study power. The next presentation would deal with dichotomous data rather than continuous data to estimate ratios, percentages, or proportions. Assalamu alaikum.